The BBC presents the ABC of the universe. The seventh and last talk in this series is given by Professor Sir Bernard Lovell, Fellow of the Royal Society of Jodrell Bank.
In the last two talks, some reference has been made to the problems which arise when we ask how the universe came into existence. Now, to end this series, I want to talk more about this so-called cosmological problem, and also to look at some of the possible answers. Wherever we look with the large telescopes, we see galaxies of stars apparently distributed throughout space in enormous numbers. Now, these galaxies contain tens of thousands of millions of stars, and our own Sun is typical of these stars, and our own home in space, the Milky Way, is typical of these galaxies. We don't know how many of these galaxies of stars exist in space. Every time man has achieved a more powerful telescope, which has enabled him to see fainter galaxies, then our ideas of the total number have increased. At the moment, the most distant galaxies identified are 4,500 million light-years distant. And within this observable part of the universe, there are certainly thousands of millions and probably trillions of these great galaxies of stars. Now, where did all these stars and galaxies come from, and what's going to happen to them in the future? This is the question which we must try to answer. And in seeking this answer, we have to explain an extraordinary thing. This is that the photographs of the distant galaxies show that the light from them is reddened, and that this change in color towards the red end of the spectrum increases as we penetrate further into space. Dr. Baldwin has already explained that astronomers interpret this as a true so-called Doppler shift, showing that the galaxies are moving away from one another with high speed. And the further the galaxies are from each other, the faster they're moving apart, until by the time we've penetrated to those distant galaxies and booties which are 4,500 million light-years away, the speed of recession is 83,000 miles a second, which is nearly 1/2 of the velocity of light. It's an awe-inspiring thought that every minute since I've been talking to you, we've separated by another 5 million miles from those distant parts of the universe. The implication of this expansion which we witness today seems to be that as we retrace time past, the galaxies must have been much closer to one another than they are now. If we retrace time in this way, we seem to be led to the conclusion that in an epoch of about 10,000 million years ago, all the material which now makes up the stars and galaxies must have been very closely concentrated in space. Was there indeed an unique condition of the universe at that time? Was there an explosion which scattered the primeval material which subsequently formed into the galaxies and stars? Now, Professor Ryle has already indicated that there is no really decisive observational answer to this question. The telescopes at the moment only take us 4,500 million years into time past, and this is less than half of the time to that possible unique state of the universe. So we have to consider if there are likely to be other explanations for the origin and expansion of the universe other than an act of explosive creation 10,000 million years ago. Astronomers began to search for such explanations in the last century, long before we gained our present observational picture of the universe and its expansion. Then, the laws of gravitation introduced by Newton were believed to govern the condition of all matter, and it was natural to use these laws in an attempt to explain the condition of the universe. Then in 1916, tremendous interest was reawakened in the problem when Einstein began to explore the consequences to cosmology of his theory of general relativity. In order to apply relativity to cosmology, Einstein introduced an arbitrary term which has become famous as the cosmical constant. Now, if you're not a mathematician, don't worry about this, but I must mention it because the point is that in this form the equations of general relativity predict a whole range of possible different universes, depending on the value which is attached to this constant. Only a few of these theoretical model universes have been explored in sufficient mathematical detail to facilitate comparison with the universe which we observed, but these few are of great interest. For example, let's look at just one other model. The Belgian astrophysicist Lemaitre has explored in great detail the consequences of assuming that the cosmical constant is real and positive, and that physically it represents a force of cosmic repulsion, which acts on the large-scale universe in opposition to the gravitational forces of Newtonian attraction. Lemaitre's picture of the evolution of the universe is this. In the beginning, the entire material of the cosmos existed in the form of the elementary particles of matter, probably protons and neutrons. This material was packed in a superdense state, which he calls the primeval atom. The size of this atom was probably about as big as our solar system is today, and the density of material inside it must have been tremendous, at least a million times the density of water. About 50,000 million years ago, this primeval atom exploded, and the basic particles of matter flew out in all directions. After several thousands of millions of years, the initial impetus of this explosion was exhausted. And at this epoch, the universe consisted of a nearly uniform distribution of hydrogen gas. During this period, the size of the universe was probably about 1 million light years, with a tendency to settle down into a uniform gaseous condition in which all the major forces were nearly balanced. Then local irregularities began to appear, the beginnings of condensations into regions of gas which were eventually to form the clusters of galaxies. Then the forces of cosmical repulsion began to come into play, overriding the forces of Newtonian attraction, so that these condensations began to move apart. The change from the nearly uniform gaseous condition to the beginning of the expansion and the initial stages of the formation of galaxies must have occurred 10,000 million years ago, and is equivalent to the explosion epoch on the model in which the cosmological constant is zero. We see that in this evolutionary model of Lemaitre's, the expansion of the universe which we witness today is not the result of the impetus of an initial explosion, but is considered to be due to the operation of the forces of cosmic repulsion. Lemaitre's theory is of particular interest for a number of reasons. Of all the evolutionary models arising from general relativity, it is perhaps the most thoroughly worked out in the mathematical sense, and Lemaitre's association with Einstein, Eddington, and the other great cosmologists of the early part of this century adds cogency to his arguments in favor of the theory. Furthermore, there are no known observational facts about the universe which are in conflict with these ideas. Other possible cases include a universe in which space first of all expands for a few tens of thousands of millions of years and then contracts back to its superdense condition, with the expansion-contraction cycle capable of indefinite repetition. The attraction of these models is that no assumptions have to be made about the beginning or ending of the universe, since the cyclical expansion and contraction is capable of indefinite extension into time past and into the future. However, these concepts of continuity have received greatest attention during the last 10 years from the theories of continuous creation, or the steady-state theory. Although Hoyle has adopted the theories of general relativity to give mathematical form to these ideas, the concepts of continuous creation are in direct conflict with the evolutionary theories of general relativity. The idea of continuous creation arises from the concept of the perfect cosmological principle, introduced by Bondi and Gould, according to which, when the universe is considered on a large scale, it presents an unchanging aspect throughout time and space. However far we move back into time past, or project ourselves into the future, the universe will be similar to the one which we see around us today. Since the universe is expanding and a constant thinning out of the galaxies is occurring, the theory implies that matter must be created continuously. The rate of creation of the primeval matter must be such that the decrease in density caused by the recession of the nebulae is exactly counterbalanced. According to the concepts of this theory, the hydrogen atoms are created out of nothing. They eventually condense into new nebulae which will replace those which are forever moving out of the observer's view. The evolutionary theories of general relativity all imply some form of singularity in an epoch of about 10,000 million years ago. Now, no such singularity is necessary in the steady-state theories. 10,000 million years ago, the steady-state universe would be the same as it is today when viewed on the large scale. The individual galaxies of that epoch will have aged and drifted away to infinity, but new ones will have formed to take their place, to give the universe its unchanging aspect. Now, this theory of continuous creation is in violent contrast to the theories based on general relativity, which lead to the ideas of some form of evolutionary universe. How can we find out which type of theory is correct? Professor Ryle explained how the radio telescopes are now penetrating so far into the depths of the universe that they are giving us information about the condition of the galaxies as they were many thousands of millions of years ago. If we could with certainty make a simple count of the numbers of galaxies in these distant regions, then it should be possible to decide which type of theory is correct. If the universe is in an evolutionary state, then the numbers of galaxies in a given volume of space at a distance of, say, 8,000 million light years will be much greater than the numbers in a similar volume close to our own region of time and space. But if the universe is in a steady state, then the numbers will be the same, because the basic postulates of this theory is the uniformity of the universe in time and space. At the moment, although we are convinced that the radio telescopes are penetrating into these regions of time and space, there's no complete agreement on the interpretation of the results. There are, of course, other observational tests which might help to distinguish between the theories. For example, on the evolutionary theories, the distant galaxies will, on the whole, be younger than the galaxies nearer to us in space, because we see them as they were in the early stage of the evolution of the universe. In the steady-state theory, there should be no such variation on the average. One thing is quite certain. It is that the radio telescopes, with their tremendous powers of penetration into the depths of space, have revived interest and enthusiasm in cosmology. For years, it's been a subject for endless theoretical speculation. Now at last, we seem to be on the verge of finding out how time and space began.
That was the final talk in the BBC series, The ABC of the Universe. The speaker was Professor Sir Bernard Lovell of Jodrell Bank.